Hey, it's Tim the Tutor here with Free Test Prep Online, and in this video, I'm going to be reviewing radical halogenation reactions, in particular of alkanes, alkenes, and of allylic and benzylic carbons. As usual, my videos are going to be full of practical information and problem solving. While I do go into some technical details, the focus is how do I help you understand how these reactions work so you can pass your tests. My videos build upon foundational organic chemistry knowledge, so I do have two suggestions before you watch this video, and those are watching the Organic Chemistry Reactions Problem-Solving Process video, as well as my Organic Chemistry Essentials Resonance video. With that being said, let's move on to radicals. Before we get into the radical reactions, it's probably a good idea to review what radicals actually are. And a radical is simply an atom that has an unpaired electron. Radicals are highly reactive because they don't have a full octet. They're created when a covalent bond is homolytically cleaved. That means each atom gets one electron. You can see on the right I have Br2. And when we apply light or heat to that Br2, we can see those two half-headed arrows, one going to each of the bromines, generating us two bromine radicals. This image shows the relationship between bond dissociation energy and increasing radical stability. When a carbon-hydrogen bond is homolytically cleaved via a hydrogen abstraction, radicals are formed. A bond is easier to cleave, that is, it has a lower bond dissociation energy, in this manner if it forms a more stable carbon radical. Like carbocations, radicals are stabilized by both hyperconjugation and resonance. Unlike carbocations, all of the allylic and benzylic radicals are more stable than the tertiary radicals. Carbon radicals, for practical purposes, are trigonal planar. You can see right next to that statement, I have a view of a trigonal planar molecule that has a radical on the central carbon. And I'm taking a side view of that molecule. You can see that it's flat. We have one group in the plane and then one group going backwards and one group going forwards. And then we have that p orbital with a single electron in it. That barely affects the shape of that carbon. So again, for practical purposes, it is trigonal planar. In addition, radicals in allylic and benzylic positions have resonance structures. On the very right image, you can see how we draw the resonance structures using three half arrows. Last, despite the many similarities that radicals have to carbocations, radicals never rearrange. So carbocations undergo carbocation rearrangements. Radicals do not have any rearrangements associated with them. All of the radical mechanisms that you're going to encounter in this video follow a three-step process. I'm going to give you practical definitions for each of these steps. We start with initiation, and all initiation is that we create the halogen radical. This is followed by propagation. Propagation is very confusing for a lot of students when they actually go to draw the mechanism. They tend to make a lot of mistakes in this mechanism because they're not quite sure what to do. The end goal of propagation is to generate a stable organic product and recreate the halogen radical. That way the reaction can keep on going again and again and again. That's why it's called propagation. The other thing that students get wrong about this is that propagation is where you get your final product in radical reactions. You do not get it from termination, because termination, all that is when we combine any two radicals, effectively removing the radicals from the system. Usually the termination step gives us weird products in very low concentrations that we can ignore. So again, your actual product comes from the propagation step. Now, there are three general types of radical halogenations. First is radical halogenation of an alkane with either chlorine or bromine radicals. The second is radical halogenation, sometimes called radical addition, of an alkene. And the last one is radical halogenation of an allylic or a benzylic carbon. All three of these radical halogenation reactions proceed via those three steps: initiation, propagation, and termination. However, they all have unique things to consider during propagation. When you go to learn the reactions individually, all the steps tend to make sense. But when you mix and match reactions from other chapters, or you intersperse these reactions among themselves, it's really easy to confuse exactly what happens in every case, especially because all of these radical halogenations are so similar. Therefore, it's really crucial to learn what the individual reactants do by consistently applying the organic chemistry reactions problem-solving process to reinforce the ideas over and over again. The first reaction we're going to review is radical halogenation of an alkene, and in particular, we're going to focus on the difference between radical chlorination and radical bromination. And as usual, anytime we encounter a reaction, we should be using our four-step reactions problem-solving process. And that starts with analyzing the functional groups on that very first molecule there on the left, an alkane. Now, alkanes are very non-reactive. They're very stable molecules. So really the only note that I would take under alkanes is that they can do radical reactions. Now that we're done with step 1, we can move on to step 2, which is analyzing our next reactant. And on the line, I see Cl2 and the delta symbol for heat. In combination, I know that heat is going to be a radical initiator for chlorine. And a radical initiator simply gets the radical started. And now I have to pay attention to Cl2, because this is going to have a unique thing to do versus bromination, which does something else. And for radical chlorination, the most important thing that you need to know about it is that it is fast and non-selective. And what do I mean by fast and non-selective? That means that when chlorine radicals go to abstract a hydrogen from an alkane, they will abstract any hydrogen. It doesn't matter how stable the radical is going to be that it's going to generate, because that chlorine radical is non-selective. Now that we've finished step 2 of the problem-solving process, we can move on to step 3, which is seeing where the overlap is in the first two reactants, and we can see that both of them can do radical reactions. So we see the overlap, and now we draw the mechanism of this reaction. And we know it's a radical mechanism, so we have to start with initiation. And initiation is usually pretty simple. We have our chlorine-chlorine bond, and then we apply the heat, and the bond is going to homolytically cleave, giving us a couple of chlorine radicals. After we finish initiation, we move on to propagation. And in propagation, we use that chlorine radical to react with the alkane. So what I'm going to do, I'm just going to go ahead and cross these out, and I'm going to put a P right in front of the alkane, and I'm going to show a chlorine radical right next to it. Now, what I cannot do here is just go about removing any random hydrogen. What I need to do is make sure that I account for all of the possible hydrogens that chlorine can abstract. So there are actually 4 unique hydrogens, and I'm going to show those now. Now you can see all of the unique hydrogens shown in blue. You may be wondering why there's not a unique hydrogen in that very bottom left carbon. That's because the top left carbon and the bottom left carbon are actually equivalent to each other, so all of their hydrogens are also equivalent. So now that we have all of the unique hydrogens drawn, we can show the steps for abstracting the hydrogen in all 4 of these scenarios. Again, it's because the chlorine radical is non-selective. So whenever we draw radical mechanisms, we always draw 3 half-headed arrows for propagation. So we're going to draw a half-headed arrow from the chlorine radical to some spot in space. The next half-headed arrow comes from the carbon-hydrogen bond. The bond, of course, has 2 electrons, and we only need 1 of them. So we're going to draw a half-headed arrow from this bond, and it's going to go and touch tips with the other radical. And I say that graphically, that way you can remember better. There's a lot of tip-touching action going on in radical reactions. Next, the second electron in this carbon-hydrogen bond is going to go to the carbon. And now we can draw the intermediate of this first step. I'm going to go ahead and do the same thing for all of the other 3 hydrogens. Now that we've drawn our intermediates, we can move on to the next step, which is the step that confuses most students. For this, we need to go back to what propagation means, and that means that we are going to get our stable organic product and recreate our original chlorine radical. So how do we do that? Well, we need to bring back in Cl2, which you should assume you have plenty of, because we didn't create every single radical in that first step. We just provided a little bit of heat to get the reaction going so that it could propagate itself. So we're going to draw another arrow with chlorine on the line and then see what happens. In this first pathway, the radical is going to abstract a chlorine from Cl2. And once again, we are going to draw 3 half-headed arrows, one from the radical to one spot in space, one from the chlorine-chlorine bond that's going to touch tips with that original one, and then the last one is going to go to the chlorine, generating another chlorine radical. And that's going to give us a product that looks like this. Now I can do this for all of the other pathways as well. So I'm going to go ahead and do that now. Now you can see that I have a product for each of those different unique hydrogens. So there we have it, 4 unique hydrogens, 4 products. Except you shouldn't let me get away with that because we're not done. Because the 4th step in the problem-solving process is to check our answer and make sure we didn't miss anything such as resonance, carbocation rearrangements, or stereochemistry. And of course, there's no resonance in any of these intermediates because we don't have any overlapping p orbitals, and we don't have carbocations, we have radicals. So we do need to worry about, however, stereochemistry. So we need to look for stereogenic centers. And in the very first molecule that we created, it's interesting because we created a stereogenic center where there wasn't one before. Originally, we had 2 methyl groups attached to this carbon. Now, there's actually a unique bond that's no longer a methyl group. We have a methyl group on the bottom, but now we have a CH2Cl on the top. So that now creates 4 unique bonds at that position. And when we created that, what we can say is that it didn't matter when it was created whether that methyl group was on a wedge or a dash. It could have been rotated in either direction. But when we add on that chlorine, that position does matter. So how do we represent that? By saying it could have been either when we added, so we're going to use this squiggly line. In the second one, we still do not have a stereogenic center. That carbon in that one position with the chlorine still has 2 methyl groups, so 2 groups are the same. In the third product, we do have a new stereogenic center. And because that radical was trigonal planar, and now it's tetrahedral, there's an undrawn hydrogen there, if you don't remember it. Now, going from trigonal planar to tetrahedral, because it was flat before, it means when we added on that chlorine, it could have been added on a wedge or a dash. So once again, we can put this on a squiggly line. And then last, we do not have any new stereogenic centers. So there we go. We actually have 6 unique products from these 4 pathways once we consider stereochemistry. And of course, we do get some byproducts from these. So we also end up generating our chlorine radical. And in that first step, we do end up getting some HCl. And again, that's just a byproduct. So that's how we do radical chlorination. You may be wondering about the termination step. And usually you don't show termination steps when you're just trying to predict the product. But if you wanted to, you can literally pick any 2 radicals that you see on the screen, draw them coming together by touching tips and creating a bond between the atoms that have those radicals. And those would be any number of your termination steps. If we had instead used bromine in place of chlorine, how would this reaction have been different? Well, once again, we're going to go back to the problem-solving process, and when we look at that first reactant, the alkane, we write down that we have an alkane that can only react in extreme conditions, such as if we have a radical. Moving on to the second step of the problem-solving process, we see Br2 on the line and heat. And once again, since we have a halogen and heat, the heat is going to act as a radical initiator. Now we get to bromine. And this is where the main difference comes in, and this is why knowing your reagents is very crucial. Because bromine is slow and selective as a radical. That's different than chlorine, which is fast and non-selective. So, now we know that we're going to do a radical reaction, and we know that bromine is slow and selective. Let's go ahead and start by drawing the initiation step in the mechanism. Initiation is going to work the exact same way that it did with chlorination. We have our Br-Br bond, and once we add heat, that is going to homolytically cleave the bond, giving us 2 bromine radicals. Now we can move on to propagation, so I'm going to write P next to the reaction, and I'm going to cross out the bromine and the heat because we know that that already formed the bromine radical. What does it mean for the bromine radical to be slow and selective? Well, with chlorination, we said that it was fast and non-selective and could abstract any hydrogen regardless of how stable the radical was going to be. With bromination, we are primarily going to abstract only the hydrogen that's going to give us the most stable radical. So in this case, if we look at the alkane, we have several primary positions, a secondary position, and a tertiary position for the hydrogens. And since bromine is only going to form primarily the most stable radical, we're going to abstract the tertiary hydrogen. So we're going to draw that by drawing an arrow from the bromine radical to a point in space, and then we're going to grab one of the electrons from the carbon-hydrogen bond, and it's going to go touch tips with that one, and then the last arrow is going to put the radical in that tertiary position. That's going to give us this intermediate radical. Now all we need to do to complete the propagation step is get back our original radical and form a stable organic product. So to get back our original radical, we're just going to take a Br2 that we had from the beginning, and the radical that we just formed is going to abstract one of the bromines. So we're going to draw a half-headed arrow from the radical to a point in space and meet up with another half-headed arrow from the bromine-bromine bond. The other bromine is going to get the extra electron from that bond. That's going to give us our final product. Of course, we always want to check our work, so we check for stereochemistry, and we note that there is not a stereogenic center on this molecule, so that should be our final product from propagation. Once again, the termination step, all that requires is that we pick any 2 radicals on the screen and combine them together to remove those radicals from the system. Once all the radicals are gone from the system, that will officially end radical halogenation of the alkane. So because there's space on the screen, I'll actually show at least one of these steps for us for termination. So let's say we had this radical here, and let's just say as soon as we exhaust most of the reactants in this reaction chamber, let's say that there is a bromine radical remaining. Well, here all we need to do is show that they will terminate by combining just like this, and that gives us a bromine in this position. Now you might be thinking, hey, that's just the product, and it is, but that's okay because we have other options for termination as well. Just because one of them gives us the product doesn't mean that we're right or wrong, but we can also have another thing where maybe 2 bromine radicals come together. So here is another possible termination step. And that would give us our Br2 back. I could also have drawn 2 of that reaction intermediate, that alkane with the radical, coming together as well. But usually you're only asked to draw 1 to 2 termination steps in a mechanism if you're asked to draw the entire mechanism on a test. So in summary, when we are comparing radical halogenation of an alkane with chlorine versus bromine, the bromine once again is going to be slow and selective, so we're only going to get a smaller number of products by only abstracting hydrogens from the most stable positions, whereas in chlorination, we'll get a bunch of different products. The next several reactions that we're going to review involve the alkene functional group. The alkene functional group is involved in radical addition reactions at both the pi bond and the allylic carbon. So let's go ahead and start by looking at radical additions directly at the pi bond. As is the case with all of my reaction videos, the first place we're going to start is with the organic chemistry reactions problem-solving process. So when we look at this reaction, the first thing we do is we make a list of everything we know about that very first functional group, which is, of course, an alkene. Now, when you first encounter alkenes in Organic 1, you learn that they have a nucleophilic and basic pi bond, and the three main reactions that we do there are additions, reductions, and oxidations. When you finally get to the chapter on radicals, you have to add a couple of new ideas, and that is the fact that we can do radical addition at that pi bond, and that we have an easily abstractable hydrogen in that allylic position. The next step of the problem-solving process is to look at the next reactant and make a list of what we know about it. So here we have HBr, which is an acid, and ROOR, a peroxide. And the peroxide, of course, is a radical initiator. Now, when we have the radical initiator with HBr, what we're going to do is radical addition at the pi bond. The easiest way to remember this is by associating this reaction with another reaction you already know, hydrohalogenation. That involves an acid reacting directly with the pi bond in a normal addition reaction. Here, we're still doing an addition. However, the radical initiator means that we're doing a radical addition. However, we're still doing it directly at the pi bond. So let's move on to step 3 of the problem-solving process, which is drawing the mechanism. And of course, since this is a radical mechanism, we should start with initiation. In initiation, the goal is to make our halogen radical. And when we have ROOR, what we do is we break the OO bond. That's going to automatically homolytically cleave itself, giving us a couple of RO radicals. And then the RO radical is going to abstract a hydrogen from the HBr. So we're going to draw our 3 half-headed arrows, just like this, and that's going to give us an ROH, or an alcohol byproduct, plus our initial radical, our bromine radical. Now that we have that, we can move on to propagation. So on the line, I'm going to just go ahead and cross out the HBr and the ROOR, and we're going to put the bromine radical right here. So now we're going to draw what happens when the bromine radical interacts directly with that pi bond. So we're going to draw an arrow from that pi bond. It has 2 electrons. Draw a half-headed arrow from that to some random point in space, and then the electron from the radical bromine is going to go touch tips with that one. Now, we do have a second electron to deal with in that pi bond, and we have a choice. Do we put that radical on the more substituted side of the pi bond, or on the less substituted side? Well, radicals, just like carbocations, are going to form at the more stable position. That means we're going to put it at the more substituted spot. So our last half-headed arrow goes to the more substituted carbon. And what that is going to give us is a product, or a reaction intermediate, that puts the bromine at the less substituted position and the radical at the more substituted position. But we're not done with propagation until we regenerate our original radical and have a stable organic product. So what we're going to do is we're going to bring in another HBr, and we're going to abstract a hydrogen from this, from the radical. So once again, we draw from the radical to some point in space, and the HBr bond breaks with 1 electron going to touch tips with that one, and the second electron going on to the bromine. This is going to put a hydrogen where that radical is, and we're going to get back our bromine radical. So now we're done with propagation. I'm going to go ahead and draw in that hydrogen, just so you know where it went. So there we have our stable organic product, and of course we're going to use the 4th step of the problem-solving process to check for stereochemistry. And there's not any stereogenic centers on this molecule, so we know that is going to be our final product from propagation. Once again, if you were just asked to draw the major product of this reaction, you'd be done. Propagation gives you the major product. Now, if you're asked to draw the entire mechanism, including initiation, propagation, and termination, we should draw a termination step. And there are several that we can choose from. Again, you just pick any radicals at all, 2 of them coming together. So we have plenty of possibilities. We can have a bromine radical with a bromine radical again. That, of course, is going to give us a Br2. We can have that intermediate from the first step of propagation interacting with an OR radical. This will give us another possible termination step, or we can draw any others. Once again, in the termination step, we don't really get a measurable product. It just ends the radical reaction. A very common test question that you might encounter after you've covered radicals in class is a non-radical addition interspersed among all of the radical reactions that you learned. So let's take a look at the difference between radical halogenation of that alkene versus hydrohalogenation and see if we can figure out how to get to a different product. So we're going to start with the problem-solving process, and once again, we're going to deal with an alkene and write down everything we know about it. Once again, we have a nucleophilic and basic pi bond where we can do addition, reduction, and oxidation, and we just learned that we can do radical addition and that we have an easily abstractable allylic hydrogen. But now when we look at the line, notice that we have HBr, which is just an acid. And if we remember, if we just have an acid, what we're going to do is we're going to do an addition reaction with the pi bond. Notice there's not a radical initiator, so students will often make a big mistake and just assume, because they're in the chapter on radicals or taking a test on the radical chapter, that this is a radical reaction, and they'll treat it the same way. But you need to have the radical initiator on the line in order to do a radical mechanism. So here, we are not doing a radical mechanism. We're just doing a regular addition. So what does that mean? Well, we're going to take this nucleophilic and basic pi bond, and we're going to draw an arrow from that to our positively charged hydrogen. Double-headed arrow. Again, we only use the half-headed arrows for radical reactions. And that, of course, is going to break off this bromine. The bromine's going to get those electrons. What that does is that is going to give us a carbocation at the more stable position. And here's where we need to be extra careful. That's a secondary carbocation. Secondary radicals, or radicals in general for that matter, never rearrange. However, carbocations can undergo carbocation rearrangements. So we need to pay attention and look out for those. And there is a way we can make this a more stable carbocation by doing a 1,2 hydride shift. So we're going to draw on that 1,2 shift. And that is going to move our carbocation to this more stable tertiary position. And now that bromine that we kicked off, that Br negative, will now go to this positive area, giving us our product with the bromine located at that tertiary carbon. And that's the difference between hydrohalogenation of an alkene versus radical halogenation. One, we get a carbocation mechanism, so that's going to put the hydrogen and the bromine at different positions than in the radical reaction, and we have to check for things such as carbocation rearrangements, which we don't need to look for in a radical reaction. A common mistake that students make is that they try to memorize every single reaction that they come across. This is a particularly bad strategy, and this often gets reinforced in this chapter in particular when textbooks and professors emphasize that hydrohalogenation is a Markovnikov addition and radical halogenation is anti-Markovnikov. That doesn't matter. The only thing that's important in both these reactions is understanding how the mechanism works. In both mechanisms, the radical and the carbocation both get placed in the more stable position. That's the more substituted position. That tells us where the other atoms get added. Understanding this will better ensure your success, especially on cumulative tests, where your memory will inevitably fail you when you have to keep track of possibly hundreds of different reactions at a time. Let's move on to another reaction, radical halogenation of an allylic carbon. Here we have an alkene reacting with NBS and heat. We're going to do the same thing that we always do. We're starting with the problem-solving process, and we're listing everything we know about that alkene. And of course, because we're talking about radicals, let's focus on the fact that we can either do radical addition at the pi bond, or that we have an easily abstractable allylic hydrogen. Now that we've labeled everything on the alkene, let's talk about NBS with heat, which could also be light or ROOR. Any of those would be fine. Here what we have is we have heat as our radical initiator. Now NBS is a molecule that we don't see very often, but we see it a lot in this chapter. And in this chapter, we learn that NBS does two things. With a radical, it abstracts the allylic hydrogen. So once the heat breaks up the NBS and creates the bromine radical, that bromine radical will then abstract the allylic hydrogen. Next, and this is crucial, NBS is also a source of low concentrations of Br2. Now that we've taken notes on our two reactants, we can see that the overlap lies with radical reactions, especially at that allylic hydrogen. So we can go ahead and draw the mechanism now. And with radical mechanisms, we always start with initiation. So for our initiation step, we have NBS. And NBS looks like this. That nitrogen-bromine bond has a low bond dissociation energy because when we create the radicals, the radical on the nitrogen is actually going to be stabilized by resonance with both of those oxygens. So this bond is actually fairly easy to break. So when we apply heat, what we're going to do is we're going to get homolytic cleavage, and we're going to create our two radicals. In particular, we mostly care about this bromine radical because the other radical is stabilized a lot by resonance and is therefore going to be pretty inactive. Now, I mentioned that NBS is a source of low concentrations of Br2. So this is not part of the initiation or propagation or termination steps, but it's important to understand how the reaction works. So I'm going to draw this side reaction over here. And I'm just going to use abbreviations. So instead of drawing out NBS, I'm just going to write NBS. And NBS is going to create Br2 for us. And again, we're going to say that this is low concentrations. So we're just going to keep this in mind. So we know that has happened, and now we know that we have our bromine radical from initiation. So now we can move on to our propagation step. So let's go ahead and draw in, we'll cross these out, and we'll draw in our bromine radical. Now we said that the bromine radical that we get from NBS is going to abstract the allylic hydrogen. And I know a question that you might have is, we've used bromine radicals a lot, and it seems to do different things in different situations. Why is that? Well, this is a more complicated question that I'll answer later on in the video. For now, and honestly for all practical purposes, it's better to just learn what each individual reactant does and work from there, rather than try to figure out, hey, I have a bromine radical, what does it do? Because it doesn't matter what the bromine radical specifically does, it matters what the overall reaction mixture contains. But anyway, we have our bromine radical, and we said that we're going to abstract the allylic hydrogen. And allylic means adjacent to a double bond. So the allylic hydrogen is on the carbon that's adjacent to the double bond. Here's the allylic carbon. So here is our allylic hydrogen. And we're going to go ahead and abstract that. So what we're going to do is we're going to draw three half-headed arrows, as we usually do, one from the radical to a point in space, one from the carbon-hydrogen bond to go touch tips with that, and the third is going to go onto that allylic position. And that is going to give us an intermediate that has a radical at that allylic position. Notice that we have a radical next to a double bond. And here, this should tip you off to the fact that we probably have to consider resonance. Now, if we don't consider resonance, there is the fourth step of the problem-solving process, which is check your work and check for things like resonance. So you should be reminded later on, if you forget to do it now, if you're following the problem-solving process, that you missed a step. But let's go ahead and draw in the resonance structure for this. I'm going to draw the three half-headed arrows to show the resonance, but I'll erase it once we move on to the next step. So our resonance structure is going to look like this. This is worth repeating as much as possible. In propagation, the whole point is to regenerate our original halogen radical. So we know we have to get the Br radical back at the end of propagation, as well as get our stable organic product or products. And this step, right after we create this radical, is where students always go wrong in this reaction. The next step involves the Br2 that we generated in low concentrations from that side reaction. So that is what goes on the line in this next step. Now the allylic radical is going to abstract a bromine from the Br2, and the second bromine is going to accept that extra electron from the bond. And we know from the resonance structures that we have a second reactive site with that radical, so we're going to do that for this bottom pathway as well. And that's going to give us these two products. Of course, anytime we get the products like this, we should check for stereochemistry. Now, the stereochemistry that we need to check for is twofold. First, we need to check for R and S stereochemistry. In other words, we need to look for a stereogenic center. And there is no carbon with 4 unique bonds in either of these products, so we don't need to worry about it this time. The next thing we look for is anytime we're moving around a double bond, in this case in the resonance, it is possible that we have E and Z isomers. However, in this case, we don't have E and Z isomers because on the left side of the double bond in that second product, we have 2 of the same group. So we don't need to worry about E and Z this time, but in other reactions, we would need to consider it. So again, stereochemistry, you need to consider both R and S for sp3 hybridized carbons, and we need to consider E and Z isomers if we are moving or creating a double bond. Now, an interesting question usually arises when students first learn about this reaction with an alkene and NBS in a radical initiator. And that question is, since we're generating a bromine radical with NBS, why can't we just generate the radical with Br2 in a radical initiator instead? Well, in radical reactions, we only need to generate a small amount of radical for the reaction to occur, because the radical will keep propagating. It'll keep making itself over and over again. The Br2 that we didn't radicalize in initiation would be our source of additional bromine radicals. So we would actually need more Br2 to be available. The problem is, if we have a lot of Br2 available, that is going to react directly with the pi bond in a non-radical addition reaction. NBS spontaneously generates Br2 in low concentrations, so that will effectively prevent the competing reaction from occurring. That's why we have to use NBS and not Br2. The last reaction we're going to cover is radical halogenation of a benzylic carbon. And this looks very similar to the reaction we just learned, where we halogenate the allylic carbon. The difference is, this reaction is actually quite a bit simpler. Most of the time when you first learn about these radical reactions, you may not have covered very much about benzene. It really depends on how your particular class is set up. So we may not have a lot of notes to take on benzene, but what we do know when we go to our problem-solving process is that we do have an easily abstractable benzylic hydrogen. And again, it's easily abstractable because when we remove it and create a radical, it is going to be stabilized by resonance. Now you may notice that on the reaction line, we have NBS or Br2. And of course, we pair either of those with our radical initiator, such as light heat or ROOR. Now we know from the last reaction that when we use NBS, we abstract the allylic position, so here we're going to abstract the benzylic position. But why can we use Br2 in this case? Well, benzene rings, due to their aromaticity, are actually highly resistant to your normal addition reactions, so here using bromine as our source of the bromine radical is actually okay. So we can use NBS or Br2 to create that initial bromine radical. Now that we know we're going to do our radical reaction, we're going to go ahead and draw the mechanism, once again starting with initiation. Here I'm going to abbreviate the initiation step, and I'm just going to write NBS or Br2. I'm going to put our radical initiator on the line, and all that I care about from the initiation step is that we are generating this bromine radical. The next thing we're going to do is propagation, of course, and with propagation, let me just cross these out for now. We're going to put our bromine radical on the line, and we're going to go ahead and abstract that hydrogen by drawing our 3 half-headed arrows, like we normally do for these radical reactions. That puts the radical on the end position of that benzylic carbon. Now, technically, there are resonance structures that I could draw, but it's not important that I actually draw them. So I'm just going to write here plus resonance structures. And the reason why I'm not going to actually draw the resonance structures is because the resonance structures on an individual level are not as reactive as that benzylic site. And that's because if we end up adding a bromine to any of those carbons on the benzene ring, it's actually going to disrupt the aromaticity of the ring and actually going to be less stable. So the only reactive site here is the one in that benzylic position. So that's the only one we actually need to worry about. So now to finish propagation, we just need to regenerate our original radical and create our stable organic product. So of course, we're just going to put our bromine back on the line. Whether we use NBS, which produces Br2 in low concentrations for us, or whether we just use Br2 directly, doesn't matter in this case. So the Br2 is going to go back on the line, and we're going to draw our 3 arrows to regenerate our bromine radical and create our stable organic product. Of course, we always should check for resonance, carbocation rearrangements, and stereochemistry, but in this case, we don't need to worry about any of those, as none of those things are going to affect this particular product. So like I said, radical halogenation of a benzylic position is actually simpler than at the allylic position because we don't need to worry about whether we use NBS or Br2, so it's less to remember, and we don't even need to worry about the additional resonance structures. So that is the only solution right there. I brought up a question a little bit earlier about the bromine radical interacting with either the alkene directly or with an allylic hydrogen. In radical halogenation of an alkene, why does the bromine radical that was generated from HBr react directly with the pi bond and not abstract an allylic hydrogen? After all, in one of the other reactions with NBS, we created a bromine radical, and we said that that bromine radical did in fact abstract an allylic hydrogen. So that's the question. So on the screen here, I am showing the pathway for reacting an alkene with HBr and ROOR. Now we've already covered this reaction. In the initiation step, we generate a bromine radical, and then in the propagation step, the alkene interacts directly with the bromine, and we form a radical on the more stable side. Then, to end propagation, or rather to continue propagation, that radical abstracts a hydrogen from HBr, giving us our final product, and another bromine radical, which we can use to continue this reaction. But the question is, why does that happen, and why don't we get this other pathway as shown here? Again, with NBS, when that was our starting material, we did abstract the hydrogen. So there's no difference between the bromine radical from NBS and the bromine radical from HBr. So why don't we abstract this allylic position? After all, it should be easier to abstract the allylic hydrogen than it should be to interact directly with the alkene, because breaking that bond forms an allylic radical, which is more stable. Let's continue this reaction and see what would in fact happen if we tried to carry this out. Now remember, with NBS, we formed a Br2 in low concentrations. Here we don't have Br2. Our starting material was HBr. So if we put an HBr in this line, the next step in this reaction is that this radical is going to abstract a hydrogen from the HBr. And what's that going to give us? That's going to give us back this alkene that we had originally, and it's going to regenerate the bromine radical. And then the bromine radical, like we said, well, we can just abstract that allylic hydrogen again. And then that allylic radical is then going to interact with another HBr and do the same thing. So in other words, what we're going to do is we're going to establish an equilibrium between the radical alkene and the radical bromine. Because of this equilibrium, that bromine radical actually has plenty of time to interact directly with the double bond, even though that reaction is probably a little bit slower. That reaction pathway, however, is not reversible like it is for the bottom pathway, so we will never establish an equilibrium, and the reaction can proceed in this manner. So that's why we write the propagation step when we use HBr with a radical initiator the way that we do, and we don't write it with the bottom pathway. Sure, the bottom pathway happens, but because that equilibrium is established, we will slowly lose more alkene to that pathway in the middle, which is the one that we show. Now, I did not read this anywhere. This is just my hypothesis for why this happens, and it makes sense so much that I'm comfortable sharing it and saying this is a good reason or a logical explanation for how this works. I know we covered a lot in this video, so let's do a recap of these radical reactions. As a student, learning the reactants and the mechanisms is far more valuable than trying to memorize entire reactions. This is true in all of organic chemistry, and this is the first time that you really start to see it in most organic 1 and 2 classes. Alkanes. They react with radicals generated from Cl2 and Br2. A radical reaction with an alkane is the only time we care about the terms fast and non-selective and slow and selective. Don't confuse this with other reactions. The pi bond of an alkene will react directly when an acid is present. When the acid is by itself, we'll get a carbocation mechanism, not a radical mechanism. When the acid is accompanied by a radical initiator, that's when a radical reaction will occur. And finally, the allylic hydrogen of an alkene will be abstracted when NBS is present with a radical initiator. Br2 cannot be used because it will cause a competing non-radical addition reaction. Benzylic hydrogens are abstracted with radicals generated from either NBS or Br2, however. If you got something out of this lecture, please feel free to like this video and subscribe to this channel. If you have any questions or comments, leave a message below. And last but not least, if you want more help or want easy access to valuable organic chemistry resources for free, be sure to check out the notes underneath this video with a link to join our community.